So what I'm going to do for the rest of this lecture is talk about the historical development of quantum mechanics and classical computing and information theory and where this fits into the class. And I'm also going to start talking about models for quantum computation. And before I start talking about models for quantum computation, let's start with models for classical computation. So models for classical computation. So can anybody give me a model for classical computation? Yeah? Turing machine. Anybody give me another? Yeah?
DFAs and MFAs.
What?
Deterministic finite automaton.
Oh. Yeah, finite automaton. Another? Yeah? Yeah, good. Another? Was there another one? Okay. What?
A coin.
A coin. Well, okay. So which of these, if any, do you think the standard quantum mechanical model for computation is? Okay. So all of you have something to learn in this class. That's good. Okay, so first let's classify these into two parts. I want to claim this is universal and this is universal, and this not universal, and this is not universal. And what does universal mean? Okay. Let's erase this. 1936, Turing. Universal computation. So what universal means is that given any computation that is reasonable, you can do it on a Turing machine, or you can do it with the lambda calculus. So that does all computations. Finite automata do not solve all problems. And coins are very far from solving all problems. Okay. And I'm going to write down a circuit model, which is actually the one which the quantum computers, it's a model that we'll be using for quantum computers, and it's the model that really is the standard one for quantum computers. And this is, well, I should say something about its universality. This is actually super universal. In other words, there are some computations which can be solved with a circuit model which cannot be solved with Turing machines. So this is a problem. But we will get back to how to fix it. So what is the circuit model? The circuit model is what you can draw circuits, which are, say, NOT gates, AND gates, and OR gates. And why don't I use these say not and and or rather than drawing the EE symbol for them, because half of you probably don't know the EE symbols and we're not going to be using them. So, and what you do is you just take your input, put it through a gate, feed the output of that gate into another gate, feed the output of that gate into another gate, and then you have the output here. And I guess we probably want several bits for the input, and an OR gate takes 2 inputs and gives you 1 output. And this is the circuit model. So why did, and these have been around a lot longer than Turing machines. I mean, electrical engineers were designing circuits well before 1936. So why did Turing not use circuits for his model of computation rather than Turing machines? Any guesses? Yeah?
The circuits get really big.
Well, yes, that's true, but that's not the real reason, because Turing machines can also, in some sense, get really big. Yep.
I mean, is it something to do, if you wanted to do like a for loop whose size depended on the input, can you do that with a circuit model? Or? I mean, aren't there things that are hard to implement on a
Right.
circuit?
Well, it's because circuits are only designed. If I give you a circuit for a finite size input, so I can have a circuit. So let's pick a problem. Multiply 2 n-bit numbers. 2 n-bit numbers. I can write down a circuit which multiplies 10 by bit by 10-bit numbers, and I can write down a circuit that multiplies 12-bit by 12-bit numbers. But if you want to have some kind of computation that is independent of the size of the input, circuits don't really do it, because circuits have, because circuits are specified for the particular input. And you can also cheat because of that. So let's see. So let's pick an example of an uncomputable problem. Does the Turing machine with, I guess, program given by P. So you can write your program of a Turing machine as a string of zeros and ones, and that's with P. And input I halt. This is uncomputable. But you can solve it with a circuit model. With a family of circuits. Circuit with 2 to the pi inputs, outputs 1 if the Turing machine halts, and 0 if the Turing machine does not halt. Because, for the circuit model, there's not a circuit for every I mean, there's not a single circuit for every size input. There's a different circuit for every size input. So we can hide uncomputable information in the design of the circuit for size n. So that's a bad idea. So this is why Turing came up with a Turing machine to do computation. Okay, so in 1994, I discovered the factoring algorithm and started talking to people about it. And somebody pointed out at some point that when they first heard me talk about it, I was using the quantum Turing machine model. And then later, by the time I gave the talk in 6 months after I discovered it, I was using the circuit model. So why was that? Well, it turns out I've been talking with physicists. And physicists, if you have the Turing machine, what you have to do is you have to keep the Turing machine in superposition, which is something I haven't told you what it is, but you need to keep the Turing machine in a coherent superposition of where the heads are, having the head in different places along the tape. And physicist just looks at it and then says, that's totally impossible. There's no way we'll ever be able to engineer that, even if it's theoretically permitted by physics. On the other hand, the circuit model you can do just by having a bunch of quantum bits in coherent superposition with each other and applying gates to pairs of quantum bits, and that actually works. Or I shouldn't say actually works. In 1994, that was also impossible, and several orders of magnitude less impossible than a quantum Turing machine. And now we are seeing people have quantum computers with, say, 50 gates, which really do satisfy the circuit model and are reasonably stable, coherent superpositions. And they're getting bigger. And so far, no one has built a single quantum Turing machine. So this is why we're doing the circuit model. So for the circuit model, the description of the circuit should be, it should be output by a classical computer program. A classical computer program. And this is what keeps you from cheating and hiding uncomputable information in the description of the different circuits of different sizes. Yeah?
Sorry, can you explain more what do you mean by the output of a classical?
Well, there should be a classical computer where the input is n, size of circuit, the output is the quantum circuit of size n. Quantum circuit of size n. And that solves the problem you're interested in. I should say for inputs of size n. Yeah, this computer can be a Turing machine. It should not, it should be some kind of classical universal computer, and it really doesn't matter what it is because this is, because they're all classical universal computers are really equivalent in some sense. Yeah?
Is there a way to fix up the rules of the game for the classical circuit model so it's not so unreasonable?
Well, you can have the classical circuit be the output of some Turing machine, but this is somehow recursive because if that gets you back to Turing machines. If you want the classical circuit to be the output of another classical circuit, you're somehow building in, you may still be building in ways to cheat. Maybe you can have a classical circuit that is of size n that designs a classical circuit of a larger size that does something, but I don't know if anybody has done this. Good question. Okay, so we will talk really about classical circuits next time, more about classical circuits next lecture.